Okay, so welcome to Math 317 Operations Research. We're completing our unit right now on linear programming. And so we're going to be focusing for the last little bit on integer programming and some of the challenges that arise from this, but as well as some of the opportunities. So we'll also get to problems such as the traveling salesman, which is one of the big problems in the subject. And so what I want to do is, I think I've said the law of the hammer before, but just to repeat, I think the last one is the most concise phrasing. If all you have is a hammer, everything looks like a nail. And there's a lot of ways to look at this. One way, as I've mentioned, is if you are really good at something, whatever you're given, you will try to make it look like something that you can do so that you can use your skills. A better way to look at this is if there's something that you're really good at, go and look at a field where people don't have this skill. Go to the land of the screwdriver. If they could have solved the problem using screwdrivers, they would have done so. They're smart people too. And I have had a very productive career working in a variety of different fields because I bring different tool sets to the problem. Similarly, when you're building your teams, you don't want everyone to have the same skill sets. It's nice to be able to discuss things with each other, but you want to be able to cover a wide variety of things. One of the big skill sets, which is often not stressed nearly enough in college, is the ability to interact and talk to people. And that is something that becomes extremely important. So what I want to do is I want to do a little bit of a discussion on how do we convert nonlinear problems to linear problems. So we've already seen a little bit of this when we've looked at the method of least squares, when we were trying to do curve fitting. Well, linear regression, it requires a line. Well, most relationships in the world are not linear, but if you do a log-log transform, you can make them linear. So the question is, can we take nonlinear relations and somehow convert it to a linear programming problem? And the answer is yes, but there's a cost. And so the cost is we have to introduce additional variables. And the question is always, how expensive is it to introduce additional variables? If the variables were real, it wouldn't be so bad. Unfortunately, the variables that we introduce are going to be binary, they're going to be integer variables. Integer programming is significantly harder than real programming. We do not have great algorithms that we know will terminate or almost surely terminate in a small amount of time. But for a large variety of problems, we can often get really close to the solution. And so for many things, given that we don't even know the true values of the parameters we're working on, if you can get close to the solution in a reasonable amount of time, that's good enough. So the big question is, what kind of constraints can we handle? So if you think about, say, the movie problem, one of the issues we had was the capacity for a room, right? A screen can only take so many people. And you have to decide which screen do you want to show a movie on? Well, what if there's more people who want to watch a movie than is capacity on the screen? What happens? So I say, somebody give me a movie, or I'll choose one of my favorites. My daughter just recently rewatched Princess Bride with some of her friends. Great movie if you haven't seen it. So let's say 250 people want to see Princess Bride, but there's only room for 150 people in that theater. What do you have to do? Well, we can't start a second screening at the same time. We only have one copy of the movie. So we have to turn away people. So what happens to those people? So what do you mean by different theater? Well, so one possibility is they might then say, I'm not going to come to your movie theater today. I wanted to see Princess Bride and nothing else. I'm going to go to another theater where it's playing. What's another option? Watch a different movie. It would be interesting to see what would you choose as another movie that might be comparable to Princess Bride. Any thoughts? How many people have seen Princess Bride out of curiosity? I might choose another romantic comedy. I might choose maybe When Harry Met Sally. So would people go and see another similar movie, or would they go and see something completely different? What do you do with those demands? When you're trying to figure out how much money the theater is going to make for showing movies, if you have more demand than capacity, do those people then shift their demand to another movie? Is the demand for Princess Bride the following, and the demand for maybe When Harry Met Sally something lower? But if the people from Princess Bride can't get in, do you recapture those people elsewhere? So we need to be able to do things such as an if-then statement. If the demand is too large, then this is going to happen. Somebody want to give me 2 action movies? Rambo.
Terminator.
And Terminator. Oh, I like the fact that you have a Stallone and a Schwarzenegger. There was a great rivalry between the two of them in the 80s. And in some of the movies, they have some very nice digs against each other. So let's say you have Rambo and Terminator playing at the same time. Each movie could have their own demand. Do you think their demands are independent of whether or not the other movie is playing at the same time? Yeah, probably not. Is that people might want to see an action movie. And so you might have a certain number of people who just want to see an action movie. A subset of these maybe prefer Rambo, a subset of these prefer Terminator. And so when you're trying to figure out what the demand is, you might want to have an if-then statement. If Rambo is playing, then the demand for Terminator must go down by this amount. If, and so on and so on. So these give you an example of why we might want to do if-then statements. So there's a whole slew of stuff that we want to do. I just wanted to try to motivate why we're doing this. So when we do integer programming, I'm going to make a couple of assumptions just to make the math a little bit easier. These are not that big. So I'm going to assume any quantity under consideration is bounded. Okay? Is this a reasonable constraint to have in the real world? Can you think of any resource in the real world that you have infinitely much of? No. I am not saying that the bound is a reasonable number. I was at a math conference this weekend, and one of my colleagues mentioned in one of their papers they had the bound e raised to the, I think, 116, which beat the largest number that occurred in any of my papers, which was only 10 to the 602. These numbers are astronomically large, but they're still finite. And so for a lot of things, we just need to know that something is finite just to limit the space under consideration. So this is not that big of an assumption. All right, the second one is we're going to assume all of our quantities are discrete with a fixed smallest unit. So if you think of like quantum mechanics, almost like Planck scales, we have things discretized. We can move h bar, 2h bar, 3h bar. If you think monetarily, what would be the smallest increment if we do things monetarily in the US? A cent, but there's one place where it might not be a cent. Anybody drive recently? Yes, we still have prices that end in 9/10 of a cent. But if you go a few digits to the left of a cent, to the right of a cent, I'm sure we're fine. And so it's not a big deal frequently to have the same discretized scale for everything. We only have finitely many things. Not a big deal. Okay. This just makes a lot of the calculations easier to just say that we're under these conditions. Okay, so here's the first one. So let's consider some quantity A. So it's bounded, so I'm going to assume it's between minus NA and positive NA. Why do you think I have the subscript A on my N?
So that it relates to the quantity.
Yeah, to show that it relates to the quantity, that I have some bound on A and that bound is determined on A. I could, of course, not bother to put a subscript and I said, look, I just have some universal bound. But it might be that if I have some information about where it lives, I can use that to make better decisions about the variables that I'm choosing. So if I know a little bit about its boundedness, I might be able to use that to help write down the constraints in a little bit more efficient manner. Okay, so I have it's bounded, and I'm going to assume A is discrete, so it can be 0, plus or minus delta, plus or minus 2 delta, and so on and so on. Right. So the following ensure that ZA is 1 if A is greater than 0, and ZA is 0 otherwise. So we'll talk about these three constraints slowly in a moment. What is ZA of A detecting? Yeah, if A is greater than or equal to 0, if basically if A is happening. And you can decide about, do you want to have A greater than or equal to 0 or greater than 0? It doesn't really make that much of a difference. This could be maybe a penalty function. Maybe if A happens, I want to subtract something. So for instance, maybe if Terminator is playing, I'm going to subtract a little bit from the demand for Rambo. And so Z of A will be 1 if Terminator is playing. And now I can multiply this by something and give myself a little bit of a decrease in the demand of one of the movies. So for many things, it's frequently useful to detect if something is happening. And I might not care just how much. I care, is it happening or not? All right. So there are 3 constraints. So I want Z to be 1 if A is greater than or equal to 0 and 0 otherwise. So the first constraint is pretty clear. Z is going to be either 0 or 1. Right? I'm trying to have Z as a binary indicator variable. And so the first constraint is Z is going to either be 0 or 1. Okay, now things get interesting. So the first constraint is I want A divided by n of A plus delta over 2n of A to be less than or equal to Z of A. And then the third is I want Z of A to be less than or equal to 1 plus A over n of A. So there are 2 cases for A. So case 1, let's say A is greater than or equal to 0, and case 2, A is less than 0. And so let's just analyze both of those cases. So let's do the case where A is greater than or equal to 0. If A is greater than 0, let's look at 2. So we have A over n of A plus delta over 2n of A. What can you tell me about the left-hand side of 2? So what must be true about the left-hand side if A is greater than or equal to 0? Is positive. So if the left-hand side is positive, what does that tell you about Z of A? Okay, so be more specific, because we know constraint 1, what do we now know about Z of A? So Z of A is in 0, 1. We know it's positive. So what must be true about Z of A? It forces Z to be 1. So forces Z of A to equal 1. Now let's look at 3. So if we look at 3, we know A is positive. What does that tell us about Z of A? So if A is positive, what can you tell me about 1 plus A over NA? Almost. It's greater than or equal to 1. So this gives Z of A is less than or equal to 1. So everything is consistent. So the effect of these 3 constraints, if A is greater than or equal to 0, force Z of A to equal 1. Okay, so forces Z of A to equal 1. Now let's look at the other situation. Let's assume A is less than 0. What can you tell me about 2? So what do we know about 2? So A is now negative. We have A over NA plus delta over 2NA. What's true about the left-hand side? I'm sorry? It's negative. Why is it negative? Good. A is going to be at most negative delta. I always hate with the negative things. When you say at most, that's actually the smallest of the negatives, right? So A is at most negative delta. So because we have a delta over 2NA, it forces the left-hand side to be negative. So what does that give us? What does that tell us about Z of A? So Z of A is greater than negative delta over 2 and A, so no information. Either 0 or 1 work here. All right, well, let's look at 3. So if we look at 3, what must be true about 1 plus A over NA? So it's less than 1, strictly less than 1 because A is negative. What else can you tell me about the right-hand side? Greater than or equal to 0. Because remember, we don't want, for instance, Z of A to be less than negative 3, because Z has to be either 0 or 1. So we now know the right-hand side is between 0 and 1. Z of A is less than or equal to the right-hand side. And since the right-hand side is strictly less than 1, yields Z of A equals 0. So these conditions force Z of A to be 1 if A is non-negative, and force Z of A to be 0 if A is less than 0. When you are programming, how many of you have decent programming experience? Okay. How many of you program directly in binary or machine language? Okay, good. Yeah, we do have support groups for people who are still doing this, right? You don't do this anymore. You have these wonderful programs. When my kids were younger, they had these little kid programs that you could put on the iPad where kids take blocks of code and it like says, you know, it's an if-then statement, and you just drag it in and you don't really have to understand how things are working. You can just build up your program by things like this. That's what you want, and that's what we have nowadays for stuff like this. You have all of this stuff is predefined in good linear programming packages, where you can just set up your if-then statements and all this stuff. And it can introduce additional variables and stuff like this. If you were going to do this professionally, you would learn how to do this. You know, if this class was co-listed, I would force you to do this. You know, I'm not going to force you to do this. I just want you to know that it can be done, and it's not that hard. These are not terrible constraints. You know, the two inequalities are very straightforward. And then we just have, you know, ZAs and 0, 1. Okay. So we now have a detector variable. All right, so the next is the exclusive OR. Can somebody tell me the difference between the exclusive OR and the inclusive OR? Inclusive is they can both be true. Would you like cream or sugar in your coffee? And what's the exclusive OR? One has to be true, but not the other. You know, do you want the Yankees or the Guardians to win? In the real world, you could, of course, want both. But you know, if we say, you know, the Yankees or the Guardians will win, you know, it's no longer personal preference. So if you want an inclusive OR, if I ask you what's your preference for who wins, that could be an inclusive OR. But at the end of the day, only one team will win, because Major League Baseball understands that it would be a sign of the Armageddon if a baseball game ended in a tie, and this will not be allowed to happen ever again since that horrible All-Star game. So it will be an exclusive OR. So here are 7 conditions that ensure that either A is greater than or equal to 0 or B is greater than or equal to 0, but not both. All right, there are 7 conditions. I think it's natural to break this up into a subset. How many groups do you want to break these equations into? So take a moment and look at these equations. I think they naturally break into a certain number of groups.
Maybe 3 groups.
3 groups. What do you think the first group is?
All the inequalities, including like ZA.
Good. So this is the first set. And the second set?
The ZB set, so that would be 4 to 6.
Yep.
And then the one that's.
Yep. So when you look at it like this, we've got, think of it as our code block from before. When you're writing a textbook or you're giving a lecture, you have to be explicit and you have to write them down. But really, it's just, I construct ZA as before using the constraints as before. So what does the first 3 give us?
That tells us whether or not ZA is positive, it's at 0 or 1.
So ZA equals 1 if A is greater than or equal to 0, and 0 if A is less than 0. Right? So what we could do, if we were doing things at a high level, is just say, construct ZA as before to be the indicator for whether or not A is greater than or equal to 0. The next one is very similar. ZB equals 1 if B is greater than or equal to 0, and 0 if B is less than 0. And now the last one is the fun one. ZA plus ZB equals 1. What does that do?
That means that only ZA and it can be 1 if it is 1.
So a little bit stronger. Exactly 1 equals 1. So only 1 happens. What if I gave you ZA plus ZB is, how might you try to do an inclusive OR? So if I do that as greater than or equal to 1, then at least 1 happens, maybe both. So when I was an undergraduate, I don't want to go into all the details, I was actually on bad academic standing and on probation after my first semester. And I had to quickly add classes to my schedule. And so I added baby logic. And 50% of the exam was state which of the following 10 sentences are true or false. And there were things such as, P plus Q implies not Q, or stuff like that. And I wanted to write all 10 sentences are truth value determinable, all 10 sentences are true or false. You use the inclusive or, and this is a logic theory class, you should know better. Given that I was on bad academic standing at the time, it was not worth taking the risk. The professor did admit that I was right. She would have failed me, but I was right. It is extremely important when you are doing the programming to think, do you want an inclusive or do you want an exclusive or? And are you in a situation where exactly one can happen or multiple things can happen? So can anybody give me another example of either inclusive or exclusive? Think about Fridays in October at Williams. Okay, so it's Mountain Day or not, so that's going to be exclusive. If you look at after the first Friday was not a Mountain Day, either the second Friday or the third Friday will be Mountain Day. Is there any chance that Maud will shock the Williams community and give us a bonus Mountain Day this year to make up for and to encourage social emotional well-being? Probably not. I'm going to email her after class. I'll see if I can get a second Mountain Day. I doubt it. But boy, would that, don't tell anybody, boy, would that surprise the community if there was a second Mountain Day this year. Right? I think that's a really good example of a exclusive or. We are not expecting to have 2 Mountain Days. So when you're doing your programming, you really want to think, all right, what else might you want to do after doing or? What other logical commands might you want? So we've done your detector, we've done or. What other connectors do we have? Okay, so we did inclusive or, which is basically the same, but the only difference is the last one is, as you said, greater than or equal to 1. If then is another natural one to do. So if something happens, then something else happens. So can anybody give me an if then situation in the real world? Good. If it's mountain day, then there are no classes. If it's mountain day, homework is now due the next day. So if thens are going to be things that you would want to code a lot. All right, so when we look at this, so we want to say, if A is less than 0, then B greater than or equal to 0. Again, some kind of detection thing. So again, I have Z is in 0, 1. All of these binary integer variables start off by a condition that says whatever you're looking at is either 0 or 1. So you always have to have that. Then we have 3 other ones. So we have nz is greater than or equal to a. We have a plus 1 minus z times n is greater than or equal to 0. And then we have b is greater than or equal to negative z times n. One of the nice things about having slides is I don't have to remember all these conditions. I can just project them on the board. And now that I have it on the board, I can just go through and see why they work. So we have 2 cases. So we remember for an if. So let's see, so let's do case 1. Let's say a is less than 0. Let's see what happens. From 2, if a is less than 0, what does 2 tell us? We have n times z is greater than or equal to a. Does that give us any constraints on z? So a is a negative number. N times z has to be greater than or equal to a negative number. No constraints on z. Z is either 0 or 1, so no constraints. From 2, z is free. Let's look at 3. A plus 1 minus z times n is greater than or equal to 0. So a is negative. Now, does that give us any constraints on z? So if z is 0, then we have a negative a plus n is greater than or equal to 0, and we're assuming a is at most, the absolute value of a is at most n. Okay, so z equals 0 works. If z equals 1, then we would have a negative number is greater than or equal to 0, which is impossible. So now z has to equal 1. And let's look at 4. B is greater than or equal to negative z times n. Does that give us anything? So z is free. Because we know z has to be 1, the right-hand side is going to be negative n, and by assumption, b is going to be between negative n and positive n. So yes.
Are we saying that z is 1 and then a is negative, so it's greater?
Well, no, because we're assuming in this case that a is less than 0. So because a is less than 0, if z happened to equal, oh wait, we want z to be 0, not 1, right?
Yeah.
Oh, sorry, yep, sorry, I wrote the wrong thing. So 3 forces z to be 0. Okay, and then what does 4? What happens with 4? So if z is 0, what does 4 do? What's the only way 4 can hold? B is greater than or equal to 0. So the only consistent way to satisfy this is B has to be greater than or equal to 0. If A is greater than 0, it doesn't matter. We only care about if the condition holds. But let's just investigate what would happen if A is greater than or equal to 0. What do we get from 2? So what would happen in 2? If A is greater than or equal to 0, what must be true about Z? I don't think 0, 1. I think we have to be. What if A, for instance, is 5? Could Z be 0? I think 2 forces Z to equal 1. So if A is 0, Z could be 0. Okay, good. Okay, so we're allowing A to be greater than or equal to 0 here. Okay, good. So if A is 0, Z could be 0. If A is positive, okay, good. So from 2, we have Z is greater than or equal to 0. Okay, good. My bad, thank you. So from 3, if A is non-negative, do we have any information about Z? We want the left-hand side of 3 to be non-negative. If A is non-negative, 1 minus Z times N is always going to be non-negative, right? And so is there anything forced on Z from equation 3? No, Z is free. And now from 4, Z is still completely free. So no matter what value of B we have, we could always take Z to be 1, and then everything is okay. If take Z equals 1, any B is okay. Do we care about the value of Z? Not really. Here we just care about making sure that B is greater than or equal to 0. Maybe B is a bonus in demand for a movie because Rambo is not showing, so now more people are going to Terminator. Okay. This is a little bit similar to Lagrange multipliers. Who remembers Lagrange multipliers from either this class or multivariable calculus? What do we use Lagrange multipliers to do? So why do we care about Lagrange multipliers? To find candidates for extreme points. Do we care about the value lambda that arises when we do Lagrange multipliers? No, it's an intermediary. It's to help us. Frequently, the best way to find the candidate points is to find lambda. But there are many times when you actually don't bother finding lambda. You might take ratios of equations and the lambdas cancel. So at the end of the day, I really just care about making sure if A is less than 0, then I'm only considering situations when B is greater than or equal to 0. I don't care about Z. So I don't necessarily care about what the value is. So always keep track of what you care about. All right, so the next one is truncation. So I have a sick sense of humor. I was preparing the slides late at night. So you have to figure out what it should be saying. Anybody want to take a stab at it? So theorem 8.4.1 truncation. Let Z be in 0, 1, yeah, right? Let Z maybe be a binary variable, which is at most NX. What do you think comes next? Okay, the following expressions on the random variable y, which equals x if x is greater than or equal to So what do you think we're trying to do? We're trying to truncate. So let's go backwards. What's the best way to try to figure out what this means? Yeah, look at the expressions that we have. So we know it's got to be following. In a math speak sentence starting FOLL, it's got to be following. So let's hold off on the rest for now, and let's just see what these different things do. So if x is less than x naught, then z equals 0. Okay. Do we know how to do an if-then statement? Yes. Does anybody have any desire to clutter up? No, right? We know how to do if-then, so if-then is going to be our box, so let's just do if-then. So we now know if x is less than x naught, then z equals 0. If x is greater than x naught minus delta halves, then z equals 1. Right, so if we're trying to think about what's going on, here is our value of x naught. If we are less than x naught, so over here, this is going to be z equals 0. If we're greater than x naught minus delta halves, then z is going to be equal to 1. So I'm going to assume, x naught is going to be a multiple of delta. So if we take delta halves, then that's going to be from this point forward. This will be z equals 1. And this will be like an open point in this direction. Z will be 0. Okay, so what is z detecting? So z is either 0 or 1. What does z detect? Z detects if x is greater than or equal to x naught, or x is less than x naught. And this would be z equals 1, and this would be z equals 0. All right, now let's look at the next one. Y minus x plus nx, 1 minus z, is greater than or equal to 0. So if z equals 1, so now we'll have two cases. I flipped everything over. So case 1 is z equals 0. Case 2 is z equals 1. Oops. So if z equals 0, what do we know from 3? So if z equals 0, we know the left-hand side has at least an nx. X is at most nx, so negative x plus nx is non-negative. So from 3, we get y is greater than or equal to 0. Right? Yes? What about from 4? So z equals 0. So what does that tell us about y? So y is now less than or equal to 0. And now what do we get from 5? So we might actually want this to say, so let's look at 5. Do you think 5 is correct as written, or do you think something might be missing? Yeah, and maybe also less than equal to x. So if I had to guess from looking at this, do you think some of 5 might be missing by looking at it? Yeah, if you look at it, the 5 in the parentheses are not going all the way down. The 0 looks like it has some issues. This could clearly be missing some things. These two things over here, these make y equals 0. And so as long as x is positive, there's no problem. So for 5, we're okay if x is greater than or equal to 0. And we will basically assume that we need equal signs here. I'll extend things out a little bit. All right, so if z equals 0, then this gives us a new variable y, which is equal to 0. Let's look at what happens now when z equals 1. So what does 3 give us now? So if z equals 1, then we get y minus x is greater than or equal to 0. So what does 3 tell us? Y is greater than or equal to x. Right? Because z equals 1, the nx 1 minus z is 0. What about from 4? What do we get? If z equals 1, we get y is less than or equal to nx. All right, so that just controls how big y can be. Not too bad. And then what does 5 give us? It now gives us y has to equal, well, it gives us y is less than or equal to x. So these combine to give us y equals x. So we definitely want the inequalities. We definitely want less than or equal to. So the following, I think I would phrase it as make the random variable y, which equals x if x is greater than or equal to x naught. Or maybe instead of makes them, maybe creates a random variable y, which equals x if x is greater than or equal to x naught. So basically, if x is at least x naught, y equals x, otherwise it equals 0. Can you give me a situation in the real world where you might have something like this? So if the demand for a flight is at least a critical level, we're going to fly it. And if not, we're going to cancel, and then we'll just put those passengers on another flight. How many have ever experienced the joys of flying out of Albany? I think a lot of times the airlines, if we need to kill flights, we'll kill some of the flights coming out of Albany. I was once in Newark where I think 4 consecutive flights to Albany were canceled. There were, I think, higher demand routes that just had more people, and when you only have a couple of planes, those planes had priority. So it could be, when you're trying to calculate what's going on, I'm going to have this flight. But if the demand is below a certain amount, then maybe I'm going to just cancel it. Or maybe you have to have a certain number of students in the class, or the class is canceled. So y is either going to be 0 if x is less than x naught, or it equals x. So, right, so for instance, maybe if we think of the revenue for the airline, we might have a certain demand for the flight. But if it's below a certain critical threshold, the flight doesn't happen and we get no revenue. So, it would be convenient to maybe have y down to 0. Or if the movie theater is trying to decide which movies to screen, if the demand is below a certain amount, it may not be worth it for the movie theater to actually go through and screen the movie. So the whole point of this is to just show you there are so many functions that are nonlinear that we can linearize. We have this truncation function that we can make linear. Well, we make it linear by introducing all these binary variables. Binary variables are not easy to work with in terms of having an algorithm that's known to be fast and arrive at the optimal solution. But if you're willing to just get close to the optimal solution in a reasonable amount of time, then binary variables are fast. So all of these problems are essentially the same. If I give you what the constraints are, it's really not that bad to just go through it slowly and just ask, what does each constraint do? Frequently, the constraints fall into two categories. If I want something to happen, then these are the constraints that matter, and some other constraints have no effect. And if I want the other thing to happen, then they flip often in terms of which constraints are actually controlling what goes on. So a lot of times, you might be in a situation where, well, this constraint doesn't really do anything if z equals 1. Okay, but when z equals 0, then it comes in. And we saw that with like the if-thens and stuff like that. Okay. I'm not going to go through all of the other ones. I think there's a limit to how many of these you can do in a day without becoming mentally fried. The point is they exist. The book goes through in detail your minima, so we can actually make sure that y is the minimum of a or b. And when you hear it said out loud, the minimum of a or b, okay, maybe the or function might be useful. And the way you would code it is we just do the constraints with the or. And of course, when I have the or there, in the background is the fact that we had to introduce additional constraints. All right, then the next one is we can have a maximum, so we can have y is the maximum of a or b. Well, again, not surprising that an or statement is going to come in. All right, and then in a shock, we can actually make sure x equals the absolute value of a. And you can view the absolute value of a as I want the maximum of what? So how can you view the absolute value of a in terms of a maximum? Yeah, as the maximum of a and minus a. So if we've just done your maximum, just take b to be negative a. And so the question is sometimes when you do these things, do you want to introduce new notation or do you want to use existing things? How many of you remember all the rules for differentiation? Everyone's hand should be up right now. This is basically, are you awake, right? Product rule, quotient rule, chain rule. How many of you remember the proofs? So you can prove the product rule by adding 0. You can also prove the power rule as a special case of the chain rule. You can prove the reciprocal rule, the derivative of 1 over f, f to the negative 1 is negative 1, f to the negative 2, f prime of x. If you know the reciprocal rule and you know the product rule, what other rule can you get immediately now? The quotient rule. So you can write f of x over g of x as f of x times 1 over g of x, and now apply the product rule to f of x and 1 over g of x. So when you're trying to decide how do you want to teach calculus, you can decide which rules do I want to prove and which rules do I want to have just as consequences of other rules. You could, of course, prove the quotient rule directly, but if I'm going to prove the chain rule, let me do as a special case this, and then this way I don't have to bother doing the quotient rule. Okay, so I think this is a good place to stop. This gives you a real sense of the fact that we are learning something that's worth learning. There are so many things that can be converted to linear programming problems that it's not that restrictive to say we're only going to look at these linear problems. We can do if-then, we can do max, min, truncation. So many different things can be converted. The problem, as I've been saying, is the cost. Just because we can do this doesn't mean we can get the optimal solution in a reasonable amount of time, but it does mean we can get pretty close. All right, so this is a good place to stop. We will continue on Wednesday. Let me stop recording.